Hello. Today we shall be speaking about a new concept I would say, in algebra. It's called composite function. And why we do study this concept is that because functions, the ones that we exposed them in our last lesson, we spoke about all the kind of algebraic functions that we meet, like the power function, and the ones that are transcendental ones, the exponential and the logarithmic ones, etc. But it's seldom that you find we call them elementary functions, the one that we are that we have to study, or the one that we shall deal with in general. But the problem is that we don't meet them in their simple way. In other words, usually you get something like, for example, e to the twice x instead of e to the x, or you get, for example, something like, as we have seen, sine 3x instead of sine x. So these kind of functions, we call them composite functions. Why composite? Because you have here two operations. You have to multiply x by 2, and then you raise e to the power 2x. And same thing with sine 3x. So in fact, you have two operations in tandem, in other words, in sequence. And these are very elementary, the one that you see, but sometimes they're more complicated. Like, for example, e to the power square root of x, or sine the logarithm of x. So you have here two operations done in sequence, and we have to see how to study this phenomena. So we call this phenomena, in fact, composite functions. So for composite functions, we shall see where do they appear, and then the existence of a composition. Do they always exist? This composition, does it exist all the time? And then we will see how to construct a composite function. Now, where do they exist? Or the appearance in models. Usually, they appear in in a variety of models. For example, in electrical model, your device, your radio, your receiver. For example, you wish to receive a certain signal. So what you do, you tune your receiver to this signal. In other words, you use a phenomena or a concept, a quality called resonance, so that you tune your receiver to special signal that you wish to receive. So you have here two operations. First one is that you receive your signal. In fact, you can have three operations. You can tune your signal to receive a particular signal, and we know in electrical engineering that, or in electronics, or in communication more specifically, that the signals are mounted on something called a carrier frequency. So you demodulate it in order to get the voice only of what you want to receive, and then you amplify it. So you may have here two operations, a tuner, then an amplifier. And so you have two operations in tandem, and this is called a composite operation. You may also encounter it in mechanical models. Like, for example, you have a factory producing textile, like garments and trousers and jackets, etc. What it does is that if it is made of linen, then you have to have linen fibers into the first engine, or the first machine here, and then you get filaments out of the first machine, and then out of the filaments, you use a textile machine to produce your garment. So again, here you have two operations in tandem or done in sequence. Also, in economic model, you may wish to produce, for example, cars. In economics, you have something called the production function. Like, for example, there are many production functions, like Cobb-Douglas, for example. These production functions rely upon ingredients, upon elements. For example, if you wish to produce something, what do? The firm relies upon mainly two things. Usually, production functions, they include two variables. One is the capital, and the other one is manpower. But there are others as well. There are the raw materials, even the administration itself, the organization. This is also one of the ingredients of your first function. So your raw materials and manpower and capital, you feed this into the factory, the first factory, or the factory itself, to produce cars. So here, X is the material that is fed into the firm or the factory to produce cars. So G of X represents the produced cars. But you may very well export these cars. So if you want to export these cars, so you have another body or organization to export these cars. So here, the first operation is to produce the cars, and the second operation is to export the cars. So you are doing two operations in tandem or in sequence. So G of x represent the produced cars, while f of G of x are the exported cars. Now here you may encounter different possibilities. Now either all the produced cars, you may export them, or some only, or even you may not export any car because you reject them or they don't meet the specifications. They may not be good, or they may be more expensive, for example. So for example, cars which come from the Far East are cheaper, so you cannot compete with them. Although you produce cars, you cannot export these cars. So here you have two operations in sequence, and you have to see when and why you can compose these two operations together, and what's the domain of this composite operation. Now, in mathematics, it's more flexible. Because in economic models, or even in real life problems, you have to implant the linen or the cotton, and then you produce textile. But you can't do it around. You cannot produce textiles and then you extract cotton. You don't do this. But in mathematics, you can do this. You can do any operation, f of x, then g of x, or the opposite. For example, here we want to exemplify how you compose two functions together. You have an f and j. F is equal to x squared minus 4, f of x, and g of x 3x minus 2. What do you do to obtain f of g of x? First of all, you calculate 3x minus 2. And instead of feeding into f of x, you feed instead 3x minus 2. In other words, to obtain f of g of x, you substitute for x 3x minus 2 to obtain f of g of x. So here is f of g of x. F of g of x, it was already x4 minus 4. F of x was x squared minus 4. So instead of x, you feed in g of x to obtain 9x squared minus 12x. Whereas if you want g of f of x, and actually the sequence is important, which is first, which operation you do first. If you do g first, this is called the inner function, and f the outer function. Here on the contrary, f is the inner and g is the outer function. So you substitute in, you have 3x minus 2 is g of x. So instead of 3x minus 2, you feed in j the value of f of x with x squared minus 4 to obtain 3x squared minus 14. So f of g of x is not equal to g of f of x, of course. They are different. It depends here which operations come first. The g, you do it's the machine which is called g, which operates first, and then afterwards the operation which is performed by the second machine or the outer machine, which is f. Now the problem is not really that simple. Why? Because you may sometimes find that there are problems. Of course, in many situations, there is no problem. Like this one here, for example. This is a composite operation. You have f and j. F here is sine x, and g of x is x squared. In this problem, we see that why there is no problem here, because the sine function, the domain of which is r. And x and g of x is also x squared. And the range of f of x is from minus 1 to 1 and lies in the domain of x squared. In other words, in order to obtain f of g of x, what do you require really? You have to, since g of x is fed into f, you have to make sure that to obtain f of g of x, that the range of x squared must lie into the domain of sine x, and this is true because x squared, the range of which is from 0 to infinity, and the domain of f is r, and therefore the range of g lies in the domain of r. So everything which comes out from f, from g, can be fed into f to obtain sine of x squared. And the opposite is also true. The sine function ranges from minus 1 to 1. And from minus 1 to 1 is a subset of the real line, which is the domain of x squared. So in fact, what you can obtain, what you do obtain out of sine x, you can always feed it into x squared to obtain sine x all to square. So here there is no problem because the range of the first function is an element, or what comes out from the first operation can be handled by the second operation. But so what is then, how do we know that a composition exists? For example, in the example that we investigated, there was no problem. But many times, actually, there are some problems like this one here. Now, it's like, for example, your factory, Your factory, you find that you produce cars. There is no problem. But can you export car? And this is the situation here. You have g of x, Now here we are seeking to obtain f of g of x. In other words, we are composing the composite function f circular j. This is called f circular j. In other words, the composition between f and j, where g comes first and then f later on. Now here g of x is equal to minus x squared minus 1. Now minus x squared minus 1, if you want to draw the graph of it, you will find that its region lies from minus infinity till minus 1. This is a parabola open from below, and then you have to subtract minus 1, 2 to get this graph here. The graph of which has a range from minus infinity to minus 1. Now from minus infinity to minus 1, this is a negative value. Can you extract a root of a negative value? You just can't. So whereas the first machine always work to obtain minus x squared minus 1, in other words, your calculator will never abstain, will never refuse to calculate minus x squared minus 1 for any x, real, whatever you choose it. When you obtain minus x squared minus 1 for any x, and you try to get the square root of which, then you would fail. Why? Because the square root of a negative value does not exist, since we are dealing with real variables. So here, what was the problem here? The problem was that the range of the first function does not lie in the domain of the first function. The range here is minus infinity to minus 1, does not intersect with the domain of the first one, of f, which is the outer function, which ranges from 0 till infinity. So the intersection is empty. It's like, as I said, you have a factory which perfectly functions, but then the car that you produce do not meet the specification, and therefore you cannot produce the car. So whereas if you want this body to work, you have to make sure first that what comes out from the production of the first factory does meet the specification of your second factory. So here we exemplify it like this. We clarify, here is the domain of the first function, and this is the function g, which maps every x into the range of the first function, which is the range of g. Then here is your second operation, which is f, which maps x into f of x. Whereas what you want really to obtain a composition is that you make sure that what you obtain here as g of x can lie in the domain of the second function, which has a d of f. Here you find that there is nothing in between. In other words, the range of g does not intersect with the domain of f, and therefore it's impossible that you have a composition f circular g. Here, this is another example which is nice to see. Here you have g of x is equal to minus x squared, and here you are seeking the square root of minus x squared. This time it works for only one particular value, which x is equal to 0, because minus x squared has a range from minus infinity till 0, and this works from 0 to infinity. So therefore here you have one arrow only for the composition for x equal to 0, and you have f of 0 is equal to 0, and this is the only composition you have. And you see here that they meet at one single point. Now, this is now a better situation where you have x to the power 2/3. This is an even function like this, and we want to calculate the square root. So you calculate g of x, and here g of x has a domain R, and of range from 0 till infinity, as we see here. So can this be taken off the square root of which? Can you calculate the square root of this value here? Of course, yeah, because the square root, the domain of which lies from 0 to infinity, and the range of this from 0 to infinity. So of course you can calculate the square root of x to the power 2/3 to obtain modulus x to the power 1/3, and this is x to the power 1/3. So actually you can obtain a composition, and the domain of which will be the domain of g, of course, which is R. Of course here, if you compare this to the produced car, all the produced cars can be exported because they meet with the specifications. But also the factory, your specification can allow for more cars. Not the cars that you have already been produced, but these which have good specification, but you may also allow for other cars which are within the specification, although you have produced a better specifications. So suppose, for example, f of x is equal to square root of 1 plus x. The square root of 1 plus x work from x is equal to minus 1 to infinity. So the domain in which, if you take, as I said, f of x, it's square root of x plus 1, the domain will be from minus 1 to infinity, although you need only those working from 0 to infinity. So what you receiving, you can feed into the f, but you can also have values which are extended from g of x. So because in this situation, all the values of which you obtain from x to the power 2/3 can be fed into the square root of x. As I said, but you can also have more. So here, if we want to study this in mathematics, we say that the range of G lies in the domain of F, and therefore the range, the domain of the composition is the same as the domain of G, which is R. Now we can show it this way. Here is the function J, and here is the domain of J, and you see that the range of J, which is this small circuit, lies in the domain of the bigger function F. So what you do, you are accepting all the values that come from here. Like for example, the factory, for example, what is when somebody is out, for example, he want to watch the exported cars, and somebody asks him what are the materials used to export these cars. I'll tell him not the produced cars, but the materials already that have been used, like raw materials, like manpower, the capital, etc. So you are taking all of these ingredients, or all of these factors, because all of them were the source of these exported cars. So here, whereas you have, this is the bigger circle here, the one in the middle, constitutes and represents the domain of F. All of the range of J lies in the domain of F, and therefore all what you get from here can be accepted, and you get at the end the range of F circular J. So if you now are looking to study what is the domain of the composition, of course it's not this one here, but it's the one that you started with. You started from here and you ended up here, and then what's here lies in the domain of the outer or the second machine. So you get all this to be operated upon to obtain the range of the composition, and of course this represents the domain of the composition. Now you may have a situation where, for example, you produce your cars, but you may reject some. Some of the cars, for example, they have a defect, or some of them are expensive. The countries, for example, some countries do not do, for example, export Mercedes, BMW, for example, but they don't export, for example, Porsche, for example. Why? Because it's expensive. So some of the cars may be within the specification, but you cannot produce them. Not that they have defect, but they are out of the specification of the exporting industry. So you accept some cars and you reject others, and the same thing is here. You have here a function g of x is equal to 1 minus x squared, and this has a domain R, but the range of which lies from minus infinity till 1. But the square root of x works only for those values under the square root which are positive, and 1 minus x squared, in some places it is negative, and it's only positive from minus 1 to 1. So what will happen, those only values of 1 minus x squared which lie between minus 1 and 1, which are from 0 till 1, are those only which I'm going to get the square root. Exactly like I said in factory, some of the cars you will take them and export them, and some of the cars you will reject them because you cannot export them for some reason or the other. So the f of g of x, this is the composite rule between f and j. First you obtain 1 minus x squared, and your calculator will never abstain of calculating this because the domain of 1 minus x squared is R, but you will take only those values between minus 1 and 1 to calculate the square root, and in which case the domain of the composition would be between minus 1 and 1 only. And here it is. This is how it goes. All of this is the domain of J, and you get here the range of J. But the domain of F intersects with the range of J. In other words, you shall only accept the shaded area in between. In other words, the range of J slash with the domain of F. In other words, those which satisfy the range of J but not the domain of F. In other words, the produced cars that are not valid for exporting, here it's this area here. You don't accept them. And similar here, those that lie in the domain of F but do not lie in the range of J, you also do not accept them. You only accept them those that you produce and at the same time they meet the specification of F. So we say that the range of J here, if it intersects with the domain of F, then there is a composition. If it doesn't, then there is no such composition. So here, what you do is that you take this part here and you feed it into only this part which is shaded here, that you feed it into F to obtain the range of the composition. Now, if one asks you what is the domain or what is the domain of the composition here, now it's like exactly in your industry. Now, some raw materials and manpower have produced a set of cars which have been rejected, so these do not enter into the domain of the composition. Only those manpower and raw materials and capital that have been used to produce the cars that you have accepted them for exporting, these are the domain of the composition only, because these are the ones that you have worked upon to produce and then to export your cars. And therefore, if we come here and this is the intersection between the range of J and the D of F, you come back again to the domain of J, you will choose only part of it to represent the domain of your composition. So now we come to the condition upon which a composition exists. The condition is that the range of J intersection with the domain of F must be non-empty. In other words, the inner function, the range of which must intersect with the domain of the outer function. This comes first, G comes first, and then F later on. Now, how to construct a composite function then? It's easy. The method of constructing a circular function F circular J, or a composite function here of F and J, where G comes first and then F. First of all, you calculate the range of J. Then, and the domain of F. And you check that they are not empty. The intersection is not. If the intersection is not empty, then you can proceed further. It means that there exists a composition. It's valid now. So what you do is that you calculate F circular J. And of course, all the students can do this. You can, instead of feeding X into F, you feed G of X. So everybody can do this. But now, the difficult task is, what is the domain of this composition? Now we are sure first that the composition exists. Now, if the range of J lies completely in the domain of F, or is a partial subset of the domain of F, then it's finished. The domain of the composition is equal to the domain of J, because of course you've taken all the cars, and all of them meet the specification. So since the range of J lies in the domain of F, so the domain of the composition is equal to the domain of J. Whereas if they intersect in a subset of the range of J, what you do is what? It means that some you reject them and some you accept them. You take a subset, what you do is that you have to go back of this intersection, you have to study it and see what is the subset of the domain of J which have produced this intersection. And then this piece or subset of the domain of J which is mapped onto this intersection is the one that you shall consider as the domain of the composition. And this is how you do it. Now we take some example. For example, obtain G circular F if f of x is equal to mod x and G of x is equal to 1 square root of minus x. Now which comes first? This one comes first. Since this one comes first, then we study the range of this one and the domain of this one. Now the range of mod x is what? The domain of mod x is this comes first, G circular F. So we study the range of the first one. We said the range of the inner function and the domain of the outer function. Here we are not studying F circular J, but G circular F. In other words, we operate F and then we operate J. So the range of F is what? All values of x greater than or equal to 0, and the domain of G is what here? All values of x less than or equal to 1. So is there any intersection between the two? Yes, indeed. The values, the intersection is from 0 to 1. Now, from 0 to 1 represents what? The intersection between the range of the inner function with the domain of the outer function. So we see what is the value of x in the inner function which has produced x, the value between 0 and 1. Of course, now the value between 0 and 1, this is the graph of G circular F. The value of G, between 0 and 1 produced from where? It's produced from the value of x fed into f of x running from minus 1 to 1. So here, to calculate G of f is easy. All you have to do here is you you feed in G mod x, so you substitute instead of x mod x to obtain this. And then you study this here. There is one easy way of doing it. Instead of calculating the range of G and the domain of F, and or the range here of F and the domain of J and CD, and going back to the function F like we did here, we can do like the students do. In other words, we start from here all the time. G circular F, you get 1 minus modulus x. 1 modulus x, what is the domain of this function? The domain of this function is x running 1 modulus x must be greater or equal to 0. In other words, x runs between -1 and 1. And once you do this, it's not enough. You didn't end the problem. You have to go back and intersect this with the inner function, which is f. Now f here is what? This is the inner function, x greater than 0. X greater than 0, and here x is lies between -1 and 1. The domain of the composition here, it lies all values of x between -1 and 1. Now here, what is the domain of the, again, now here we have f of x is equal to mod x, which is the first function. The first function which operates is square root of mod minus x. Now you have two possibilities of doing this. Either you investigate the intersection between the range of the inner function with the domain of the outer function. And once you obtain the intersection, you're going back to f of x, mod x. What mod x, how you obtain a value of x such that mod x runs between 0 and 1. It's here. If mod x runs between 0 and 1, which is the function that we saw before, then x must lie between -1 and 1. And this is actually the domain of the composition. Or a better way of doing it is that you just write G circular F to obtain square root of y minus root x. And then you investigate the domain of which is -1 and 1. And then you intersect this with the domain of the inner function. Here the domain of f of x is mod x, is R. So the intersection of this with R gives you the same value, which is the domain of the composition. Here it asks you what is here. It gives you the composition directly and asks you what are the functions that constitute this composition. Of course, here there are many alternatives. You can, for example, take f of x is equal to cosine x, and then g of x equal to square root of x, and h of x equal to x squared plus 1. And here, what you get here is you get three composition: f circular j circular h. Or you reverse what you do. You take x squared plus 1 is equal to h, and g of x is equal to square root of x, and f of x is equal to cosine x. Here it's simple. Why? Because here you want, for example, f circular j. In other words, this works first and then this one. Now the range of the first function of g is what? Is from -1 to 1. Does -1 to 1 lies into e to the power x, which has domain r? Yes, indeed. So directly f circular j is the function e to the sine x, and e to the sine x has domain r. Why it has domain r? Because this is the domain of the inner function, which sine x. Sine x has domain r. So you seek now, there is no problem, because all what is you get out of sine x can be fed into e to the power x. The domain is the domain of the first function, which is r. And even if you, and this is actually what you have as periodic function. This is the periodic function of what you have. E to the sine x, which range between e to the 1 and 1 over e, because e to sine x range from -1 to 1. So some e to the raised to the power from -1 to 1, you get e, and you get 1 over e. Of course, you can also obtain G circular F. In other words, you operate F and then you operate G. So here, which comes first? This one. So you investigate the range of this one, the range of e to the power x from 0 to infinity. Does the open interval from 0 to infinity lies in the domain of sine x? Indeed, because sine x has a domain R. So there is no problem. The domain would be what? The domain would be the domain of the inner function e to the x, which is R. So here you have sine e to the power x, which has a domain equal to R. And again, here is what you get here, sine to the e to the power x, and it's a sinusoidal function, but it goes very quickly because e to the power x, it's a growing function very quickly. So, and because the sine range between -1 and 1, so the range also between -1 and 1. Here is a different problem. Here f of x is equal to square root of x, and g of x is equal to square root of 1 minus x. Now he wants what? G circular f. Which comes first? F. So f comes first. Now we calculate the range of f. The range of f is from 0 to infinity. And the domain of G, it's from minus infinity to 1. So is there any intersection between the two? Yes, indeed, it's from 0 to 1. So we go back from 0 to 1 to the first function. From 0 to 1, f of x from 0 to 1, what does this correspond? What x corresponds in f of x to give you values between 0 and 1? It's the value from 0 to 1 too, because the square root of from 0 to 1 is from 0 to 1. So the domain of the composition is also from 0 to 1. This is another nice example. Now here you have g of x is equal to x divided by x plus 1, and f of x 1 over x. Which you want first? You want f circular g. In other words, you operate g and then you operate f. In other words, you investigate the range of this one and the domain of this one. If the range of this one lies in the domain of this one, then you are free and the domain is of the domain of this one. If there is intersection, then you find this intersection. Now, what is the range of this function? Now, the range of this function is equal to r except minus 1. Why is that? Because if you put here 1, you get x is equal to x plus 1. In other words, 0 is equal to 1. So, which is impossible. So the range of g of x, of g, is r except 1. Now you intersect with the domain of f. The domain of f is what? Is r except 0. Is there any intersection between the two? Indeed, yes. It's r except 0 and 1. Now you go back to the inner function, r except 0 and 1. Here, first of all, you calculate f of g of x. In other words, instead of x here, you feed in x divided by x plus 1. So you get x plus 1 divided by x. Now here, f of g of x here, you want the domain of this. The domain of, what is the domain of x plus 1 divided by x? Provided that the range of j is intersecting with the domain of f, and you have to exclude all values of the domain of f circular j, except 0 and 1. You get r except 0 and minus. So here you have 0, and here we have why you have minus 1 here? Because already you divided in g, you performed g first. So when you did perform g first, you have to divide by x plus 1. So you have to exclude minus 1. So from here you exclude 0, and from here you exclude minus 1. Of course, there is a simpler way of doing this. All you have to do is start, as I said, you start from here. For the student, there is no reason why you complicate matters. All you have to do is that you calculate f of g of x, and then you start from here to investigate the matter. Here, you exclude 0, and then you exclude also minus 1. Why? Because once you exclude 0, you have to go back and intersect with the domain of this one. What is the domain of g of x? It's r except minus 1. So you have to exclude also the values of minus 1. So exclude both. Obtain g circular f here. This comes first than this one. The best thing, as I said, for the student, there is no need to study the intersection. What you do is that this comes first than this one. First of all, you calculate directly. You start from here. From the third step here, you calculate g of f of x. In other words, you feed this here. In other words, you have, instead of x, you put 1 over x, and instead of x here, 1 over x, and from this you get what? You get 1 divided by 1 plus x. So what is the domain now of this composition? You have to realize this from here. You have to exclude x 0 here, because 1 over x. And you have to exclude also from here 1 over x plus 1 is equal to 0. So exclude minus 1. Or you can, easy than this, you can study this one here, g of f of x. Here you exclude minus 1. And then you go back and you intersect this with the domain of the first function, the inner function here. The inner function here, you have to exclude 0. So from here you exclude minus 1, and from here you exclude 0. So you exclude 0 and minus 1. Obtain f of g of x if f of x is equal to square root of x, and g of x is equal to x squared minus 4. So again here, as I said, you start from where? You start from here. You want f circular j. So f circular j, you feed instead of x, x squared minus 4. So you start from here. F of g of x, instead of x, you put x squared minus 4. Now, what is the domain of it? X squared minus 4 must be greater than 0 because you are under the square root. So x must lie between either in the union of the two sets from 2 to infinity or from minus infinity to 2. But you are not finished. You have to intersect this with the domain of the inner function. What is the inner function? The inner function is g of x, x squared minus 4. So the intersection between this has domain R to the intersection is the same, minus infinity to 2, minus 2, and 2 to infinity. Here, this is a nice example. You have f and you give you j, and you want the composition here to constitute the equation of a circle. So all you have to do is that instead of x here, you substitute square root of 1 minus x squared. I'm sorry, instead of x here, because g of f, instead of x, you substitute 2 plus x. So if you do this, then you get here square root of 1 minus 2x squared. Of course, here you have to investigate the domain. You have 2 plus x squared less than 1. In other words, the modulus of 2 plus x less than 1, which lies between, it means that you have to, if you do this, you request that the modulus x plus 2 is less than 1. So lies between 2 and 3, etc. And then you square, you have y squared. You square this here, so you get a circle of radius. Of course, the equation of which this is a circle of radius equal to 1, and the circle is equal from minus 2 to 0. With this, we come to the end of this lesson, but I wish here to summarize what we have done. First of all, we said that most of the functions in real life problems, they usually appear in form of a composition. Now you have two operations, and these two operations, this is what you have to gain from this lecture. You have two operations. One comes first and then the second one. Now the one which comes first, sometimes it works all the time. But the problem when it works, you cannot operate then the second one. To make sure that the second one operates, is that you make sure that what comes out from the first operation can be fed into the second operation. In order this to happen, to occur, the range of the first function must either lie totally into the domain of the first function, or at least it intersects with it. If it lies completely, then all what comes into is fed into the first operation would constitute the domain of the composition. But if it intersects only with the domain of the second function, then the intersection, you have to go back and show those parts only of the domain of J which constitute the domain of the composition. But then, in order to obtain the composition, what you do, you calculate f of g of x. And the easiest way to do this, you have two ways. You have a difficult way. In other words, you have to calculate first the range of the first operation or the first function, and do intersect it with the domain of the second function. And you choose those parts. If the intersection exists, then the composition exists. And then you go back to study what is the part of the domain of the first function that constitute really the domain of the composition. Or there is a better way of doing it, and this is what we done in the late example, is that all you have to do is that you do a mechanical way. You calculate f of g of x. Suppose g comes first, and then f. You calculate f of g of x. Once you calculate f of g of x, you start from f of g of x to study the domain. And after you study the domain, you intersect this domain. You are not finished yet. You intersect this domain with the domain of the inner function. And then the intersection would be the domain of the composition. Again, you have a first operation g, for example, and second operation f. So you calculate just f of g of x. You feed this into that. And then you calculate the domain from f of g of x, you calculate the domain. And then you are not finished yet. You intersect this domain with the domain of the first function. And then the intersection of this would be the domain of the composition. So with this, we have exposed an important concept in calculus, because we shall be using these composite functions all the time. All our functions are composite, and in order to differentiate functions, we use rules for example, like the chain rule, etc., that deals with composite functions. So composite functions are all the time present in calculus. So at the end of this lecture, I wish to thank you for your attention and remind you again that all these lectures are found on the Unituno platform that you found on the internet, and I wish you good luck in your study. Thank you very much.